My pleasure to introduce today's speaker, Dr. Philippe Landry. He did his bachelor's from. Can you hear me?
Yeah. Yeah, there is some background noise.
I am also hearing that background noise. Now
Everybody switch off the audio.
Now it is very clear.
Okay, go ahead.
Okay. So it's my pleasure to introduce today's speaker, Dr. Philippe Landry. He did his bachelor's from Queen's University, Kingston, and then he did his master from University of Guelph, and he did also PhD also from the University of Guelph. And then right now he is postdoctoral fellow at University of Chicago, Illinois. And his interests are really very diverse, starting from the equation of state of dense matter to the gravitational wave and tidal deformability. And he is recipient of several awards like Alexander Graham Bell Fellowship, and he has got the best thesis prize. Today he is going to tell us about the recent development in the field of gravitational wave and the tidal deformability. So please, Philip, please.
Okay, thanks very much for that introduction, and sorry again for the slight delay in getting started here. So yes, my name is Phil. I'm a postdoc at the University of Chicago. I work on gravitational waves and the neutron star equation of state and tides in compact binaries. And for today's talk, Bharat asked me to give a review of the LIGO-Virgo collaboration's paper that placed some constraints on tidal deformability from GW 170817. So I will discuss that paper first, and then I will also mention a couple other works that I've done that deal with related things. So we're going to get started then by looking at this paper, which I hope you can see on my screen share here. It's GW 170817, Measurements of Neutron Star Radii and Equation of State. So this paper here is the follow-up to the initial detection made by the LIGO-Virgo collaboration of the binary neutron star merger that produced GW 170817. So in the initial detection paper, the analysis did not assume that both bodies involved in the merger were neutron stars. So they kept open the possibility that one or both were black holes. And by doing the standard Bayesian parameter estimation, where they have some waveform model that depends on source properties like masses, spins, tidal deformabilities, in that initial detection paper, they were able to constrain the binary tidal deformability, which I'll explain in a minute, to be less than 800. But in this paper, the LIGO-Virgo collaboration, of which I'm a member, by the way, was able to get tighter constraints on tidal deformability by assuming explicitly that both compact objects involved in the merger were neutron stars with a common equation of state. So let me say a bit about the tidal deformability, and let me see if I can bring up another slide here. Let me see. Here we go. So the tidal deformability is an equation of state dependent parameter. It's a property of the neutron star, and it imprints on the gravitational waves that are emitted by the merging neutron star binary. So here we go. Let's blow this up here so everyone can see. All right, so the tidal deformability is a decreasing function of the neutron star mass, and it correlates strongly with the stiffness of the equation of state. So basically, if there are larger pressure gradients in the equation of state of the neutron star, you get a larger star for a given mass, so a larger radius for a given mass. And this means that when you apply some tidal field onto your neutron star, like the one that is sourced by a companion in a binary setting, it's easier to deform the star. So the stiffer the equation of state, the larger the tidal deformability, and this tidal deformability will measure the induced tide on the star. So on this slide I'm showing here, you see a plot of this tidal deformability parameter lambda as a function of mass for different equations of state. And the key feature is that it is monotonically decreasing. And for equations of state that are stiffer at a given mass, the tidal deformability will be larger. So how does this actually imprint on the gravitational waveform from the compact binary? I have a little cartoon of this. So here at the left, we have our compact binary. And if you look at the acceleration gradient on one neutron star because of the gravitational field of the companion, which is non-uniform across the star, you see, of course, that the near side is accelerated, more towards the companion than the far side. And if you switch into the rest frame of the neutron star, what you see is this differential pattern of deformation, which has a characteristic quadrupole shape. So the star is stretched along the axis connecting it to its companion and compressed in the other direction. And so this gives the star a quadrupole moment, a mass quadrupole moment Q, which is measured by this parameter lambda when you describe the tidal field, when you describe the induced quadrupole moment in units of the applied tidal field. And the factor of m to the fifth here is just to make this parameter lambda dimensionless, just to make up units. So the meaning of the tidal deformability is that it tells you about the amplitude of the induced quadrupole moment in units of the applied tidal field. So how does this actually imprint in the gravitational waveform? Well, as I'm sure you're familiar, in general relativity, there's a quadrupole formula for the power radiated in gravitational waves. And in the compact binary, the fact that you have 2 point masses orbiting, at some separation produces a time-varying quadrupole moment for the system. And then with 3 time derivatives of that quadrupole moment, you get the power radiated in gravitational waves. Now, when you induce a stellar quadrupole on each star, those stellar quadrupoles will just add to the orbital quadrupole moment. And so you end up sourcing a little bit more gravitational radiation than you would otherwise. And in this way, the binary dissipates orbital energy a little bit faster, which accelerates the coalescence slightly relative to the merger of point particles. And so what you end up seeing in the waveform is a phase shift that is proportional to the tidal deformability, because basically the larger the tides, the faster you reach merger, just through this effect where you dissipate slightly more energy. So that's how the tidal deformability imprints in the waveform. And when the LIGO-Virgo collaboration, detects a gravitational wave signal by using some post-Newtonian model for the waveform, or more generally a post-Newtonian model that also has some input from numerical relativity, what you can do is a Bayesian analysis for the source properties of the compact objects that are involved in the merger. And tidal deformabilities appear in the waveform phase in the way I just described there. Okay, so now let me talk specifically about what is new and exciting about this paper here by the collaboration. So as I mentioned, the initial detection paper did constrain the tidal deformability, but it constrained this binary deformability, which is like a mass-weighted average of the deformabilities for the individual stars involved in the merger. And so this binary deformability is specific to the merger GW170817. In this paper here, the collaboration presented constraints on the tidal deformability of a canonical mass neutron star, so a 1.4 solar mass neutron star. And this is a generic constraint on the equation of state. It's saying that any equation of state must produce a tidal deformability for a 1.4 solar mass star that is within the confidence interval presented in this paper. So The main difference in this work compared to the last one, as I mentioned before, is assuming explicitly that both compact objects in the merger were neutron stars with a common equation of state. And so what this buys you basically is, if I show figure 1 here, so here is the inferred posterior probability distribution on the tidal deformabilities of each star. So the shaded green region is showing, posterior density. So the greener parts are more likely after the observation. And you see that there's a large gray shaded region here. So in the initial analysis, this region was not ruled out because it was possible that one of the stars was a black hole. But here, by assuming both stars are neutron stars with a common equation of state, because the star labeled 2 is taken to be the less massive star, and because lambda as a function of mass is monotonically decreasing, as I showed before, this means that lambda 2 is always going to be larger than lambda 1. And so right off the bat, with this common equation of state assumption, you rule out basically half the parameter space in lambda 1, lambda 2. Additionally, by assuming the common equation of state, you enforce a particular form for the correlations between lambda 1 and lambda 2. So in this plot, there are all these gray lines here, which are the lambda 1, lambda 2 values for particular candidate equations of state, given the uncertainties on the masses observed for GW17. And so the common equation of state assumption basically forces the lambda 1, lambda 2 data to lie along one line like this, so some line like this. And so basically by incorporating these correlations, the confidence region is much reduced in this analysis versus the detection paper's analysis. So in the detection paper, the 90% confidence interval was this orange line here, but by making this common equation of state assumption, the 90% confidence interval is reduced to the green line here. So in this respect, right off the bat, through making this assumption, this follow-up analysis was able to present tighter bounds on the component tidal deformabilities, as well taking this posterior and basically making a Taylor expansion for each tidal deformability around the canonical mass. One can determine the canonical value of the tidal deformability. And so one of the important constraints to come out of this work was the fact that canonical tidal deformability is about 200 in terms of median value, with error bars that go up to about 600 and down to 70 or so. And so the idea is that any viable equation of state, should be consistent with this inference of the canonical tidal deformability, and these error bars are presented at the 90% confidence level. So that was the first thing that this paper did, but I think really the innovative thing that was done here was to actually directly constrain the equation of state itself. So to attempt a direct inference of the pressure density relation inside the star from the gravitational wave data. And the way this was done in the paper was to assume the equation of state is, cold, barotropic, so just pressure as a function, and to make some sort of parametric model for the equation of state. So some parameterization. So the simplest way to do this would be to assume that the equation of state is piecewise linear in this pressure density log-log plot. So this is what would be called a piecewise polytrope approximation. And so in this model, the equation of state has 3 segments, which are just linear. And so the first derivative is discontinuous, but the function itself is continuous and monotonically increasing. And so if you make a parameterization for the equation of state in this way, what you do is in your waveform model, where normally you expect to have source properties, in particular the tidal deformabilities, you can replace the tidal deformabilities with the phenomenological parameters of your equation of state model. So in this example, this would be the 3 slopes of the piece pressure at the first dividing density between the segments. And so if you replace the tidal deformabilities in the waveform model with these equation of state parameters, which are related through the perturbed TOV equations, so the field equations that govern the structure of the neutron star. By replacing the tidal deformability model, you infer directly these equation of state parameters. And then what you do is you have some likelihoods for the parameters, and you simply reconstruct the associated equations of state using the parameterization to build up this posterior distribution shown in green here in figure 2 over the equations of state themselves. And so in this paper, that's exactly what was done, except that the parameterization used was a slightly more complicated set of basis functions than I described. It wasn't exactly this piecewise linear thing. In fact, it was a spectral decomposition, but those are just details. The point is, some parametric model was assumed for the equation of state. The parameters were inferred directly from the gravitational wave data, and then the equation of state was reconstructed to give this green shaded posterior distribution here. And so what's interesting to note in this figure is in pink with the dotted lines, you see the contours of the prior on the equation of state. So these are just, this just comes from the ranges of parameters selected with no weighting by the likelihood of the gravitational wave data. And then after you involve the gravitational wave data to weight the particular sets of parameters by the likelihood inferred from the gravitational waves, you get the green posterior distribution. And there's a definite softening of the posterior relative to the prior around twice nuclear density. So just as that lambda 1.4 constraint where the median value was around 200 is pointing to a relatively soft equation of state, here we see in terms of the equation of state itself some sort of softening versus what the prior is representing, which is somehow a reasonable range of equation of state behavior. Right. So once you have this posterior distribution over the equation of state, you can go ahead and compute posterior distributions for the equation of state dependent properties of the neutron stars, in particular, the radii of the two stars involved in the merger, because you see the equation of state in this posterior, you integrate the TOV equations for the mass and radius, and associate the likelihood for that particular equation of state to the result. And so doing that, you build up a posterior in the mass radius plane, shown in the right-hand panel here of figure 3. And here, the blue is just the heavier component, and red is the lighter component of the binary. What you end up seeing is that the inference of the median and 90% confidence interval, this posterior distribution, shows you that actually radii are consistent with being equal to one another. So the radii of the stars are basically, very close, if not the same. And the median value is about 12 kilometers with error bars of about 1.5. So again, this is saying that for these masses, which were about quite close to canonical mass, quite close to 1.4 solar masses, this is a radius value that is not excessively large. It's reasonably soft and well within the sort of expected range here. So the other thing you can do is infer the central densities and pressures of the stars, which you get directly from, directly from the equation of state posterior here. And so that's basically what's shown in these side panels here, inferring the sense of component 1 and 2 of the merger. In this paper, the pressure at particular densities, so nuclear density, twice nuclear density, and 6 times nuclear density, was also extracted with a 90% confidence interval, so that, again, equation of state models can be compared directly against that. You can also turn around and take these this posterior on the equation of state, and in this radius computed, you can compute the tidal deformabilities with the blue curve, here, the 90% confidence interval in figure 1, which is very close to the original green curve, which was inferred without using this equation of state model. So just by assuming a common equation of state of some sort that's not prescribed, without prescribing any parameterization for the equation of state, you get the green. And then if you use this parameterization for the equation of state to infer the equation of state directly, and then go back and calculate the associated tidal deformabilities, you find a perfectly compatible constraint. I think that's a pretty good overview of the results in this paper. Maybe at this stage I will pause, and if there are any questions about this paper specifically, I'm happy to answer them, and then I can talk about the other two that I wanted to mention. Any questions?
Yes, actually, what actually these right and upper panel represent in figure 2 and 3? I didn't get exactly. Yes, in figure 2 and figure 3, the right panel and the upper panel, what they actually represent, I didn't get exactly. Yes.
Gotcha. Okay, so let me try and explain. So first in figure 2, let's look at the upper panel. So this is the probability of the central density, okay, of one or the other stars. The more massive star is blue and the less massive star is orange. This is the probability of their central density being above the density that is shown on the x-axis here. So the way to read this is that the odds of the central density being above twice nuclear density, are less than it being below here, because the distribution drops off at twice rho nuc.
Okay.
And then similarly on the right-hand panel, it's the same sort of thing, but for the central pressure. And then if we look at figure 3 here, right, so in the panels here, they're showing the marginal probability distributions, marginal posterior distributions for either the mass here or the radius. So this is just integrating away, the radius uncertainty here and integrating away the mass uncertainty here. And what you see are basically here, the blue is just the marginal mass distribution for the heavier component, and red is just for the lower component, the less massive component. And then you have a similar thing here. I'm not entirely sure why this analysis produced a bimodal distribution. So the difference between the right and left panels here, I described the right-hand panel where you first infer the posterior distribution over the equation of state, and then use that to calculate the distribution over radii. Another way to proceed is actually just to get the tidal deformabilities, like through the green posterior shading in figure 1. And then you can actually use this so-called universal relation between the tidal deformability and the compactness. So that's the dimensionless mass to radius ratio. And this is just an empirical formula that shows that the correlation between compactness and tidal deformability is actually virtually independent of the equation of state. And so if you get a posterior distribution over the component tidal deformabilities, and you have some measurement with uncertainty for the component masses, and use this universal relation to infer the radius independently of the equation of state. And so that's what was done in the left-hand panel.
Okay,
the posterior distribution ends up being compatible.
Okay.
Yeah.
So the radii and masses of these component of the binary, they are constant from this maximum probability, right?
Yeah, so the quoted values are typically medians with 90% confidence intervals, but they will be taken from the marginal distributions, yeah, shown in the side panels.
Okay, thank you.
Any other questions on this paper? Okay, so if not, let me just, sort of reiterate the punchline of this analysis. So the main punchline is that based on GW 170817, the equation of state of neutron stars seems to be relatively soft, at least compared to most nuclear theory models. So if you just take a quick glance again at figure 1, different nuclear theory candidate equations of state are shown in gray, and the peak of the posterior distribution for the component tidal deformabilities is at the soft end of these equations of state. So that's the main punchline. And then if you want to sort of fine grain it a bit more, this paper has given all kinds of constraints on neutron star observables, which can be used for model selection on the equation of state, in the sense that if you have a preferred nuclear theory model, you compare it to these constraints, and you can compare it to, in some sort of Bayesian framework, to the posterior distributions given for the observables, and you can, compare Bayesian evidences to do model selection to find which is the preferred candidate model. But this paper went a step further and also tried to, infer directly this pressure density relation inside the star. Okay, so that was the LIGO-Virgo collaboration's analysis of the equation of state from gravitational waves. I want to mention now an alternative way of doing this direct equation of state inference that me and Reed Essick, who's another postdoc at the University of Chicago, recently came up with. And so this is, the title of the paper is Non-Parametric Inference of the Neutron Star Equation of State from Gravitational Wave Observations. And the point of the paper is to actually try and avoid doing this phenomenological parameterization of the equation of state, and to instead use a non-parametric representation. And so the reason we think that this is important is if you have very sharp features in the equation of state, like first order phase transitions, in case that it can be difficult for parametric methods to recover those sharp features. So for example, if you are using this piecewise polytrope where your equation of state is basically piecewise linear, in that case, if your phase transition happens in the middle of one of your linear segments, that's a feature that's going to be, smoothed out basically and will be difficult to recover. What you really want is some representation of the equation of state where the error doesn't sort of scale with whether your parametric model is well suited to the data or not. Or, alternately, it doesn't scale with the number of parameters you need, because of course you could just add more piecewise segments to your piecewise polytrope, and maybe you'd be able to resolve this feature, but it's computationally expensive to always be going back and changing your model, which means in the parametric analysis, rerunning your gravitational wave parameter estimation every time you have a new equation of state model. So in this slide I'm showing here, what you see actually is two representations that are parametric. So there's the piecewise polytrope fit I described, and then there's also this spectral method, which is actually in practice what the LIGO-Virgo paper used. So these are parametric ways to represent the equation of state, and here's how they do in fitting particular equation of state data. And so in the top right panel, what you see is an equation of state without a strong phase transition. The spectral fit does a decent job. The piecewise polytrope obviously has discontinuous first derivative. Here we're talking about the adiabatic index, by the way. But decent job of recovering the equation of state data here. But with the first order phase transition, what you see is that both spectral representation and piecewise polytrope representation essentially gloss over this key feature. And so we were motivated by this, Reed and I, to come up with a non-parametric approach, which at the very least has completely independent systematics, so it can corroborate the existing analysis, but hopefully can actually do better at these kinds of features. And the fundamental representation we use for the equation of state is something called the Gaussian process, which is commonly used in machine learning, although we're not doing machine learning per se. But it's just a useful way to represent an uncertain function. And I will, briefly explain what Gaussian processes are here, and then I'll explain how we actually use them to infer the equation of state. So you can think of a function as some collection of values at points in its domain. So here we have some function f of x. We discretize its domain, in this case, to 3 points, and we have function values at each point. And so the easiest way to think about an uncertain function or unknown function is imagining that there's some probability distribution for its value at each point in the domain. So, for example, there's a Gaussian distribution at each point, and one realization of this function is just drawing simultaneously 1 point at each point in the domain from these distributions. However, a true function is not just a collection of random variables. There's also correlations between each point. And so what a Gaussian process does is it gives you a prescription for both the uncertainty at each point and also the correlations between each point. And it does this just with a simple multivariate Gaussian model. So at each point you have Gaussian uncertainty with some prescribed mean and variance, and then you also have a covariance matrix that tells you how different points are correlated. And so the key thing about a Gaussian process is that it gives you this prescription where one realization is a random function, but with correlation. So it's not just a random collection of points. Now, the interesting thing is that you can actually condition or train a Gaussian process on underlying knowledge of the function. So in the case of the equation of state, we know the behavior of the equation of state, below nuclear density or so. And we have also observations, of neutron stars and other things that give us information about the equation of state. And so you can actually condition the Gaussian process on known data about the function. And so all this means is where previously you had your Gaussian process is telling you what the joint probability of drawing a particular value at 0.1 in the domain and 0.2 in the domain and 0.3 in the domain. By conditioning, what you're saying is, give me a prescription for the values at 0.1 and 0.2 given knowledge at 0.3. So it's really just taking what is a joint distribution here for function values at points xi in the domain, and turning it into a conditional distribution over here where you're asking for the values at those points given some knowledge at other points that are shown here with the starred index. So this is just a straightforward application of the definition of conditional probability once you write down this multivariate Gaussian distribution that tells you the correlations between all the points. And so going one step further, you don't even need to condition on sort of absolute or precise knowledge of the function at a point. If you have multiple sets of input data, so multiple sets of knowledge function, you can actually, in a sort of weighted way, condition on multiple sets of input. And so in the application with the equation of state, what we're going to use as our training data, our input data, are tabulated candidate equations of state. So we say effectively that the equation of state is our unknown function, but we have some partial knowledge or uncertain knowledge of it thanks to nuclear theory models. And so we write down some Gaussian process where we actually specify the form of the correlations by choosing a covariance kernel. We make a standard choice called a squared exponential, which depends on two hyperparameters, as we call them. So these are parameters that control not the equation of state themselves, but just the correlations within these random functions. So they somehow control the functional types of allowed functional behavior rather than the form of a particular equation of state itself. So we can specify the correlation amplitude, sigma squared, and the correlation length scale, L squared, where basically what this kernel is saying is things that are closer together, so points that are close to get together in the domain are more strongly correlated, and the degree of correlation we can set, as well as the length scale over which the correlations persist. And basically, by choosing this correlation and these hyperparameters in the way that we want, we can tune the Gaussian process to stick very closely or to vary quite freely relative to the input equations of state. So multivariate Gaussian model for the probabilities of function values at each point. We condition on different candidate equations of state, and we are able to tune through this covariance kernel whether all the realizations of the Gaussian process, which are random functions, look exactly like what we trained on, or somehow retain similar functional behavior, but are allowed to vary more freely. And so in our application, then, we actually use this Gaussian process model for the equation of state as essentially a generator of random equations of state that are nonetheless viable in the sense that they're automatically causal and thermodynamically stable, and they resemble the candidate equations of state. So they will have correlations that persist over a similar length scale. And, if we train on things that have first order phase transitions, the functional behavior we get out will have a similar feature to a first order phase transition. And so in our application, basically it serves as a generator of what we would call synthetic equations of state. So things that resemble the training equations of state, but are a bit different. And so on this slide here, there's just some technical details of how we actually implement this. The important thing is that we actually implement the Gaussian process not in pressure density space, but in some auxiliary variable space to ensure this causality and thermodynamic stability. Then maybe I'll switch back to the paper here to explain what we do with that. So let me bring that up here. So the idea is, now that we have this Gaussian process representation of the equation of state, which I will show here, in this figure 2, what you're seeing is this auxiliary variable phi, which is related to the sound speed for the equation of state against pressure. And so we construct the Gaussian process in this space, but then convert from effectively sound speed to pressure versus density, which is shown at the right here. We train on the red equations of state, which come equipped with error bars that we infer actually through a different Gaussian process. And the resulting Gaussian process is the gray shaded region back here with the black median. And so what this gives us is that one realization of the process is some function that is drawn from the shaded gray region that is going to resemble in its functional behavior the red curves, but will not, be exactly one of them. And so when you take this Gaussian process prior and map it to pressure density space, you get the prior on the equation of state that's shown either in dark blue or light blue, according to our hyperparameter choices in the covariance kernel. So this plot is very similar to the one I showed in the LIGO-Virgo paper, where we had the green posterior distribution for the equation of state and the pink dotted lines for the prior. So this would be our prior on the equation of state. And the red here again are the equations of state we're training on. The dark blue shaded region is if we tune the hyperparameters so that there is very little freedom in our synthetic equations of state to depart from the candidate ones it was trained on. Whereas in the light blue, we tune the hyperparameters, for instance, to have a short correlation length scale and a small correlation amplitude, so that the equations of state are freer to do what they want, but nonetheless, you'll notice that the median for the light blue shaded region is still basically overtop the bulk of these red curves. So the Gaussian process is effectively a way of generating random functions for the equation of state, but ensuring that they're not so crazy that they will not give a 2 solar mass neutron star, for instance, or tidal deformabilities that are reasonable. So it's a way of sort of excluding crazy functions that do not look at all like what's predicted from nuclear theory. So once we have this Gaussian process prior for the equation of state, then we do an analysis that's quite similar to what I showed in the previous paper. So basically what you do is you pick one realization of the Gaussian process. So one random equation of state, which we call a synthetic equation of state. You associate two masses that are consistent with the event GW170817, and then you integrate for the tidal deformabilities. Once you have the tidal deformabilities, you can go ahead and compare, let me see here, you can go ahead and compare the gravitational wave likelihood for tidal deformabilities. So that's what's shown in green here in this plot. You compare the gravitational wave likelihood for the tidal deformability with the value you have calculated from your equation of state. So in this right-hand panel of the plot, for a particular synthetic equation of state, maybe the lambda-1, lambda-2 combination you calculate for the masses consistent with GW17817 falls where these gray crosshairs fall. And then all you do is you read off what the likelihood of that particular combination is from the green gravitational wave likelihood, and you map that back onto the parent equation of state. And so iterating over this process where you draw, millions of these synthetic equations of state, you end up building up a probability distribution, a posterior distribution over the equation of state. So let me scroll down and show the results for that. Here we go. Okay, so these are the results for GW17817. Here in green is the gravitational wave likelihood, like I mentioned. If you take our prior on the equation of state without weighting, by any data, you get this blue 90% confidence contour out here. And after you weight by this green gravitational wave likelihood, you reduce the posterior area to this red region here. And in terms of the equation of state itself, what this translates to is in the left-hand panel, this light blue prior, which is this I showed in light blue above. You associate tidal deformabilities with each equation of state and read off the gravitational wave likelihood, mapping it back onto the parent equation of state, but you end up with the pink posterior. And so from GW17817, we see again the same feature of twice nuclear density, a softening in the posterior relative to the prior. And on this plot, the contours are the inferred central densities for, let's see, it's the inferred central density for the heavier component. So M1 in the prior versus the posterior. So basically the difference, in this method is all about how one designs the prior for the equation of state. And we think that by having this non-parametric Gaussian process model for it, it is actually more transparent and flexible in terms of how you set the prior. So suppose you're very interested in the question of whether there's a first order phase transition equation of state. Well, one thing you can do with this Gaussian process prior is, on the one hand, train the Gaussian process only on hadronic equations of state, and then set up a different prior where you train only on equations of state with first order phase transitions to quark matter. And if you run the analysis on each of those separate priors and compare the evidence for each prior, so the Bayesian evidence that you would calculate from the gravitational wave data, you can do model selection on this sort of intrinsic feature of the equation of state. If you wanted to do the same in a parametric model, you'd have to figure out how having a first order phase transition at any density or any pressure would map on to these phenomenological parameters for the equation of state. And in fact, you might have to design a different parameterization that is better adapted to first order phase transitions. So one of the main advantages we think of this non-parametric method is that it allows for dedicated model selection. So, if you're interested in some sort of microphysics feature that does not necessarily shine through in a simple way in the overall behavior of the equation of state, you can still do model selection for it just by training the Gaussian process on the appropriate candidate equations of state. Okay, so that's basically what I wanted to say as an overview of this paper. I will pause again for any questions about it. So feel free to ask. Okay, if there are no questions,
Okay,
then I will.
Please go to figure number 7. Hello. Yes. Figure number, yes, yes. So I got your point, but somehow I missed something. What are these loops in the figure? Okay, I got your point. Is prior and posterior, all these things, and this equation process, all these things. But what are these loops inside this shaded curve?
Right. So these contours here that I'm showing,
Yes,
right?
yes, 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 yes.
Right.
These contours.
So right. So this is the inferred central pressure and central density for the heavier star involved in GW 170817. So these are the same features that were shown in the upper and lower panels, upper and side panels in the previous paper. Here they're just
Okay.
overplotted on the data. But what this is saying is that for the heavier mass component of the merger, the central density is likely just above twice nuclear density or so, something like that.
Okay. Okay.
And the other thing that this figure illustrates, so there's two panels. This illustrates two different Gaussian process priors. So what I was describing, where the light blue one, the equations of state are allowed to do pretty much whatever they want. So this is what we call the model agnostic prior versus the model informed prior, where we design things so that they are more closely tied to the candidate equations of state we feed in. And what you see in the model informed case is that actually they're sort of so constrained that there's very little change going from prior to posterior. And the sort of moral of the story in trying these two different priors is that from gravitational wave data from this single event alone, you can't actually find a strong preference for either prior. So what this is telling you is that with only one gravitational wave event, any results that you extract, whether it be directly on the equation of state or on observables like tidal deformability or radii, are going to be sensitive to your choice of prior. So you have to choose wisely.
Okay.
Any other questions here?
I want to know one thing, that how the various, the nuclear physics input at the low density are accounted for in this kind of calculation.
Yeah, that's a great question. So both in this work and in the LIGO-Virgo paper, the low density equation of state is just assumed, there's some matching that's done to some assumed low density equation of state, which in both cases is the SLY model, I think SLY4. And so this is just a fixed crust model that everything is matched to. So we're not using unified equations of state as yet. However, going forward, me and Reed have actually been discussing with Sanjay Reddy and his postdoc, Ingo Taves, about adopting their low density equation of state. So they have an equation of state up to about nuclear density that comes with error bars that are informed by theory. So I'm sure you guys are probably more familiar than I am with it, but there's some perturbative scheme where you can, successively include smaller and smaller effects from, nuclear interactions while retaining this, knowledge of the size of the next order contribution. And so in this way, you get the low density equation of state with meaningful error bars. So we're actually going to be working with them to incorporate this description of the low density equation of state.
Okay. Actually, why I'm asking this question, that recently, SCUM model was basically fitted to the low density equation of state obtained from chiral effective field theory. Now, but for that SCUM model, the maximum mass is 1.7.
So, right. So one thing that we do in, I think, this analysis and also LIGO-Virgo's analysis is all the equations of state that are in the posterior must satisfy this two solar mass bound on the, lower bound on the maximum mass. So the prior may include things that, don't satisfy that. but they're basically thrown out. So the original prior you would draw would have these things, but you end up throwing them out in the analysis.
No, but my point is that if the low density Kirchhoff state has some, inaccuracy, that you will be compensating by modifying the high density Kirchhoff state.
Yeah, I understand your point, right. So it's certainly true that, unless you calculate a unified equation of state, it's possible that there are these incompatibilities. I think in the specific choice of the SLY model, it happens to satisfy this two solar mass constraint. But more generally, there have been studies that have been done where you look at a particular high density equation of state and vary the crust model, within ranges that are compatible with constraints on the symmetry energy and symmetry energy slope or something. And you find that the effect of the crust equation of state on observables like tidal deformability contributes, maybe a 5% variation or so. So at least for tidal deformability, the crust has an effect, but it's dominated by the core equation of state.
That's true. That's true. That's true. Yeah. Thank you.
Any other questions here? So if not, I will mention one other paper briefly here. This is work that I've done with Bharat Kumar. Here, the idea is trying to constrain neutron star observables without actually resorting to a model, whether parametric or not, for the equation of state. So we want to be able to produce constraints from gravitational waves on radii, on tidal deformabilities, without actually modeling the equation of state. And the way we do this is to use these so-called universal relations, which came up earlier in the talk. So these are empirical relations between, for example, the moment of inertia of a neutron star and its tidal deformability. So each of these quantities depend individually on the equation of state. However, the relation between them turns out to be virtually independent of the equation of state. So independent up to, a sort of scatter in the relation of 1%. So effectively what you can do is if you measure the tidal deformability using this universal relation, you can get the moment of inertia of the same star, up to 1% error or so. So we harness these universal relations to take the canonical deformability measurement from that LIGO-Virgo paper I showed and translate it to constraints on other properties like moment of inertia, dimensionless spin for pulsars, for which the rotational frequency is known, and radii. And so the key to this is that there are universal relations between the properties of one star, like moment of inertia and tidal deformability, but there are also universal relations between tidal deformabilities of two different stars. So these things are called binary love relations. And these were discovered by Ken Tyagi and Nico Yunus. And the idea is that if you know the tidal deformability of one neutron star, and you assume that all neutron stars have a common equation of state, you get the second star's tidal deformability for free up to some error, as long as you know the mass ratio between the two stars. And again, this is some sort of empirical relation which has been found, and it has to, it comes out of the fact that when you assume a common neutron star equation of state, all the tidal deformabilities have to lie along some function lambda of m, some tidal deformability mass relation, and the correlations between different points along a given function are actually independent of the specific equation of state that prescribes that function. So the point is that you have a prescription here that tells you if you have measured tidal deformability for one star and you have a second star for which you know the mass ratio between the two, you can get its tidal deformability for free with small error. So what we've done in this paper is to combine this binary love relation with other universal relations for properties like moment of inertia and tidal deformability to actually translate this lambda 1.4 constraint from GW17817 to constraints on tidal deformability, moment of inertia, and radius. And so just to show a couple of plots briefly, in figure 4 here, what we have are constraints on the tidal deformability mass relation that are inferred using the binary love relation and the GW170817 measurement of canonical deformability, which is on this plot, the green shaded region, but only at this 1.4 mass line here. So we take input, basically these error bars and this median, and you're able to sort of project this into the lambda versus mass plane using these universal relations. And so these are constraints that are independent of the particular model for the equation of state. They just come from these empirical relations. But the expectation is that any model that is consistent with GW170817 must fall in here. And you see a few candidate equations of state plotted in black here. Similarly, you can get constraints on the dimensionless moment of inertia. So this is I divided by mass cubed in dimensionless units. And you find a similar constraint in pink, by the way. This is the moment of inertia for the primary component of the double pulsar, which we were able to infer, specifically because it's of interest for electromagnetic observations. And finally, we have the same thing in the mass radius plane, where you see that just from these universal relations, without modeling the specific equation of state, you can constrain the radius to be basically between 9 and 13 kilometers, in a quite wide mass range from about 1 to about 2 solar masses. So that's one thing we did in this paper. We also made specific predictions for systems that have been observed in radio or X-ray. This is basically just by extracting bounds from here, although we do account for the errors in a Bayesian framework. And so the idea is that, if you have some prediction for the moment of inertia of a system, which you can then go out and measure with conventional astronomy, you can compare the gravitational wave prediction for the property to the direct measurement. And if there's some discrepancy, that means that the universal relations have failed. And there can be basically two reasons for this. There are some sort of very strange or unusual equations of state that appear to violate the universal relations. So these are things with multiple first-order phase transitions or with unusual phases of matter like crystalline quark matter. And so any disagreement between the gravitational wave prediction and the directly measured value could be evidence for one of these equations of state. The other way is if gravity is described by modified theory instead of general relativity, because the universal relations can be different in different theories of gravity. But the really interesting thing in this paper is that these universal relations give you a way of combining electromagnetic radius measurements for neutron stars in low mass X-ray binaries with GW170817's measurement of tidal deformability. And it gives you a way of doing so without having to model the equation of state. So you could, of course, do a joint Bayesian analysis where you have some, parametric model for the equation of state, and you, instead of just calculating the likelihood of the parameters from one observation, you calculate it from many observations, including EM data. Here, we're able to get, effectively the same kind of constraints on tidal deformability, but without resorting to a model for the equation of state simply from these universal relations. And the way this works is basically we have a universal binary love relation, which gives us tidal deformability at a given mass in terms of the canonical deformability measured in GW170817. We can then use a universal moment of inertia tidal deformability relation to get the moment of inertia. And then finally, we can convert moment of inertia to compactness, which, if we know the mass of the neutron star, gives us the radius. So basically, we use different universal relations successively to infer the radius based on the canonical tidal deformability measurement independently of the equation of state with small amount of uncertainty. And what this allows us to do in particular is use this relation in the other direction. And so take a radius measurement for one of these low mass X-ray binary neutron stars and map it effectively into a canonical deformability measurement. And so we have access to the posterior distribution on lambda 1.4 from GW170817. This is the green curve. This is the same thing that I showed. I showed the lambda 1 versus lambda 2 version in the first paper. This is if you just extract what it means for canonical deformability. So that's in green. And then mapping through that lambda 1.4 radius universal relation, you can take simultaneous mass and radius measurements for these neutron stars and figure out what those measurements translate to in terms of lambda 1.4. So here in gray and in orange, there are the measurements for different systems. And what you get basically when you combine the likelihoods for these electromagnetic measurements, indirect measurements of lambda 1.4 with the direct one from GW170817, you get this blue posterior distribution. And so what you end up seeing is that the median of the distribution is about the same as it was with the gravitational wave data alone, but the error bars at the 90% confidence level are dramatically reduced. And so in particular, we go from, let's see, do I have it here? 190, here we go, 190 plus about 400 minus 120 from GW170817 alone to 196. So the median has hardly changed, but now the upper error bar is only about 100 and the lower one is only about 60. And so what this is saying is that when you take into account mass radius measurements for some neutron stars, you end up sort of reinforcing the evidence for a relatively soft equation of state with canonical deformability somewhere around 200, with error bars, down and up by about 100. So you end up reinforcing that. The error bars get smaller. And the other interesting thing is that because lambda 1.4 is a unique feature of the equation of state, what you would expect if all these electromagnetic observations were equally accurate is that all the maxima a posteriori should line up in the same spot, because these are effectively measurements of the same quantity, which has one value in nature. But you see that there's actually this spread in values. And this is a sign that there are some sort of systematic errors that are affecting these radius measurements because they are clearly not equally accurate. And so, one idea we sort of mentioned in this paper but didn't really pursue yet is, well, can you somehow use gravitational waves and these universal relations to calibrate these radius measurements? So anyways, the point of this paper was just to constrain neutron star observables, but without modeling the equation of state, so that you can then do model selection on your favorite nuclear theory candidate equations of state. So that's basically all I had prepared for today. I'm happy to take all kinds of questions if you have any, and thanks for listening.
When you say that if you know the tidal deformability for one star, you can get the tidal deformability for other star for free with some small error, do you assume that the radius of both the stars are more or less same?
So you don't have to make any assumptions about the radius. Let me see if I have a plot of this relation here. Let's see. Right, okay, so here is one plot. Right, so in this plot, what we have done is we're fixing the mass of one star to 1.4, and then we are allowing the other star's mass to vary freely. That's what's showed on the x-axis here. Mm-hmm. And you get these different fits according to the value of lambda 1.4. So in the original formulation of the binary love relation, the three ingredients are lambda 1, lambda 2, and the mass ratio. For our particular application here, since in GW170817, we have measured lambda 1.4, we've basically just specialized one of the masses to 1.4. And then your three parameters are this canonical tidal deformability and then the deformability of your star of mass m. And so all you need to know are those three, two of those three parameters, and you get the third for free, basically up to the error that is shown in the lower panel. So what you see with the error is that it is very low near 1.4, and it rises if you depart, further away from a 1.4 solar mass star, getting to about 30% for a one solar mass star, and rising to, I think, almost 50% for a two solar mass star, which admittedly is, more uncertainty than other universal relations, which are consistently at the percent level uncertainty, but it still gives you a prescription for the error, and the error is, well below 100%, basically. And so, yeah, so all you need to know are lambda 1.4 and the mass of the star you're interested in this case, and in the original Yagi-Yunis formulation, you just need the mass ratio and one tidal deformability.
In the experiment, normally we get the tidal deformability for kind of average kind of number, which is a weighted average of the tidal deformability of two different stars. So from this average value, when we extract the tidal deformability for a single star, I mean, how much correct it is actually?
So, right, so you're talking about, this binary deformability, which is usually called lambda tilde, and this is a measurement. Sorry, go ahead.
Yes.
Right.
Yeah,
okay.
yeah, I'm talking about lambda tilde only. Yes, you're right. Yeah.
Right. Okay, just wanted to check. So yeah, so that parameter is something that is specific to, the merger, specific to the gravitational wave signal that is detected, because it's a mass weighted average of the two component deformabilities. And so you can transform analytically from one to the other as long as you have some likelihood functions for the individual component masses. Because basically, if you know the individual component masses and you know this lambda tilde, you can recover the individual component deformabilities. And so, there's basically a Bayesian framework for doing that. And so I don't think the mapping from one to the other actually introduces any uncertainty. The thing is that in the gravitational wave signal, we are most sensitive to this lambda tilde combination, but that does not, give complete information about the tidal deformability. So there's actually a higher order term in the waveform that is like some, in the way that lambda tilde is like a symmetric combination of the two with some mass weighting, there's actually a higher order sort of anti-symmetric contribution, which we are really not sensitive to. And so this contributes to the error bars that you end up getting on either the component deformabilities as opposed to lambda tilde, which we can actually measure quite well.
Okay. Can you please give me some reference where I can get this detail that how this value of lambda tilde is mapped to the likelihood function as you mentioned just now? Can you give me some reference for this particular detail?
Sure. Yeah, let me. I'll link something in the chat here. Let me just look it up. Are there any other questions in the meantime?
No. I mean, from my side, no.
Hello, Philippe.
Hi.
This is Bhuya. So I have some comments. It's not a question. I want some comments on this regard, because when you go to calculate the moment of inertia, right?
Mm-hmm.
The dimensional moment of inertia, which is a function of a lambda, in your equation log I tilde is equal to that sum over Cn log lambda to the power n or something, right?
Right.
Yes. If I follow that TOV equation and then solve that, find the value of lambda and nu, then we proceed for the calculation like solving the Einstein equation by rotational Newton star code. Then what is the difference, means how much accuracy in this equation or by solving the RNS equation to go proceed for a moment of inertia?
Right, good question. So here we are assuming that the stars are rotating slowly so that we take into account order chi, so dimensionless spin, spin to mass squared ratio, order chi corrections and not order chi squared corrections. So when the dimensionless spin is small, the corrections that enter at spin squared are order 1% or so, and this is where the order at which the spin affects the quadrupole moment of the star. So we're dealing with slowly rotating neutron stars, which, as we ended up finding, even for the millisecond pulsars we consider, ends up being a pretty decent approximation. So if I look here, I think it's the next table. We inferred dimensionless spins for millisecond pulsars based on GW17817. And of the 7 or so we studied, the largest dimensionless spin, so spin to mass squared ratio, is about 0.15, which I think is still sort of reasonable to treat in this slow rotation approximation. But yes, in principle, there would be spin corrections to the shape that order spin squared that would affect the moment of inertia computation.
Okay. So if the star is rotating high speed, then the mass will be changed, radius will also change, which is affected the lambda. Then we also get the change in the moment of inertia, right?
Yeah, that's right. There'd certainly be a change in the moment of inertia. The definition of this lambda is effectively that it's defined for non-rotating stars. So you would actually see, what you'd see is in the waveform phase, there would be contributions from other tidal parameters, that we wouldn't call lambda, but unless you were modeling them, you would certainly confuse them with the tidal deformability.
Okay, thank you.
So just to follow up on the previous question, if I can find the chat here, let me see. This is a paper where I believe this lambda tilde parameter was introduced, and so this might be useful for seeing how it relates to the individual component tidal deformabilities, and they also do a Bayesian analysis there. So I think that'll have what you're looking for.
Okay.
Any other questions? So if not, I will thank you for listening again. And of course, if you think of anything to ask, feel free to follow up by email afterwards.
Yeah, I also would like to thank you. It was a really wonderful discussion. I really learned few things. So it was really very nice. Thank you very much, Philippe.
Very happy to hear that. Thank you.